Okay, so the groups I talked to seem to have a pretty good idea of what was going on with these eclipses. But the main idea is that if you have your model, if my face is the sun for now, the thought is if it's a new moon, if this moon is between the Earth and the sun, so a new moon, you can get a solar eclipse because the moon can block the sun. If you have a full moon, so the Earth is between the sun and the moon, you can get a lunar eclipse where the Earth blocks the moon, moves through the shadow caused by the Earth. And of course, if everything was happening in one single plane, we would see eclipses once a month. We don't, because the moon's orbit is slightly tilted going around the sun. So we only see eclipses about twice a year, so ish, kind of depending. And then there's also the issue that the moon shadow is a lot smaller than the Earth shadow because the moon is smaller than the Earth. So solar eclipses, you need to have things lined up just a bit better, and they don't occur in large areas of the Earth. They only happen in very specific areas. So that was why back in 2017, that solar eclipse, everyone made a very big deal about the fact it was going through so much of the United States, because that doesn't always happen when solar eclipses happen. Often they're out in the middle of the ocean, and so you need a boat to see them. And just for a little dose of daily terror, if you know everything else happening wasn't enough, here's just a little map of everything else besides the moon that's kind of around the Earth. So these are all the near Earth objects that were mapped as of November 2016, so there are more now. But this white line right here is the Earth's orbit. And then you've got Venus and Mercury and these blue ones, and the sun is right here and Mars out here. The green objects are objects that are like not crossing the Earth's orbit, we're fine. Yellow objects are like, they get a little close, but we're okay. And the red objects are objects that are actually crossing the Earth's orbit. So these are things that we watch for, asteroids and stuff, to make sure they're not gonna crash into Earth. They're not, we're fine, but there are more than you might expect kind of nearby. Okay. So now that we've gone through a little bit of modeling of the Earth and the moon, we're going to shift our focus to the actual Earth and moon and think about what's happening on these two bodies. So I'm going to start just a little bit on the Earth. We have a very nice thing called the atmosphere. So this is it keeps us alive. It's slightly frustrating if you're an astronomer because we would like to peer straight through the atmosphere, but it's pretty good for anything that breathes oxygen. There's a few different layers in the atmosphere. This is also going to be kind of one of our last labs is a planetary atmospheres lab, so some of the stuff might come up in that lab as well, but the big idea is that there's multiple layers in our atmosphere, and those layers have different temperatures, different makeups, and we can see different things by looking through them. So troposphere is where we are, and it's where most of anything that all the clouds are. It's warmer, closer to the ground, and then cools as you go up and you get to higher pressure or lower pressures, sorry. And then there's the stratosphere, mesosphere, and thermosphere. I am not a, climate scientist, so this is kind of as deep as we're going to get into the different layers of the atmosphere, is that there are layers. Don't worry, I never expect you to memorize any of these, but just as a little, oh, sorry, there was a question about, from one of my previous slides, asking if we know how often two things crash into each other in the solar system. I don't know that number off of the top of my head. Sorry, I didn't have the chat open. It's open now. It's not incredibly often, and especially like so big things at least, it's not incredibly often. And we'll look more into cratering in our next class, so I'll try to get that a better number. But there's actually, I think it's something like 1%, 10%, somewhere between 1 and 10% of like the dust you will see on your car is like space dust that's from little micrometeorites getting blasted in the atmosphere and then landing on a car. So there is stuff coming into our atmosphere all the time. Most of it is just very small and burns up in the atmosphere, and then we no longer see it. So big things crashing, not often. We've, not too long ago, a comet crashed into Jupiter, but that's the main one I know of off the top of my head. So not super often, especially now. We'll look more into cratering next class, but it's not something to be overly concerned about. So I'll try to get a better number though for Tuesday. Good question. Kind of bouncing around. So back to the weather, we'll talk about this a little bit more when we get into the giant planets, but the big reason I wanted to talk about weather is because studying weather on Earth will help us understand weather on any other planet. And I like thinking about weather on other planets more because we don't have to deal with it here, which is nice. So there's a few things that kind of cause weather on Earth, and that's the rotation of the Earth, and then these different cells that we see. So as the Earth rotates, we get winds either going west or east along different specific latitudes. And then we also get things called Hadley cells, which are where near the equator, warm air will rise, so it goes up, as that warm air has to go somewhere. So it goes up at the equator, and then as the Earth turns underneath, sort of, that air gets kind of pushed towards higher latitudes, and then cools and falls at higher latitudes. So we get these kind of cells where warm air is rising, the Earth is rotating, that air is cooling and ending up at higher latitudes as the Earth rotates, and then falls because cold air falls. Warmer air is slightly less dense, so it will rise. This is why if you're in a second level apartment, it's often really hot in the summer and cooler in the winter, and still it's really hot in the summer and you want to be in the basement in the summer, and then in the winter, the upper levels will be warmer and your basement will still be really cold and you'll want to go to the higher levels in your house. So warm air rises and we get these kind of cells of rotating air. And that's also, we see this in Earth. There's also 2 cells on Venus, and then there's a bunch of cells on Jupiter and Saturn. So we can use what's happening on Earth to compare to the other planets. Weather gets really complicated really fast, and it makes my brain hurt, so I try not to talk about it too much. The other thing, this is something in one of your reading quizzes, but we can also look at in Earth's atmosphere, we can measure some of the effects of life. So unlike any other planet in our solar system that we know of so far, we're the only one with life. So there's a few things that we can look for. This is also thinking about aliens. If we wanted to look for life on other planets, we might look for these similar signatures in the atmosphere. So that's cool. But there's a few things that life does. So plants, algae, all that kind of stuff remove CO2 through photosynthesis. And that's thanks to blue-green algae, originally, which grew in the ocean, started taking some of that CO2 out of our air, which decreases the amount of greenhouse gases in the atmosphere and allows Earth to be at a habitable temperature, unlike Venus and some of the other, which we'll talk about next week when we talk about Venus. Venus has a lot of CO2, and that's part of the reason even that Venus is not habitable, despite the fact it's pretty similar to Earth. Another effect of life is that we humans are throwing a bunch of CO2 into the atmosphere through the burning of fossil fuels. Again, I'll talk about this a little bit more when we talk about Venus, but this causes greenhouse effect and global warming, which isn't great. We can also see that depending on what's happening on the surface of the Earth, that'll kind of change the temperature of the atmosphere, because buildings, roads, skyscrapers, and water are really good at reflecting light, whereas trees and grass and other things are better at absorbing light. So if we're reflecting sunlight, we're kind of heating up the atmosphere more. If we're absorbing sunlight, we might be cooling down the atmosphere more. So life can have a bunch of different effects on our atmosphere, and that could potentially be things that astronomers might look for in the atmospheres of other planets, exoplanets, that could be signs of life on those planets, which is cool. So that's just a quick run through of what's happening in the atmosphere of Earth before we get into the surface and interior. Does anyone have any questions about that? And this is just, like I said, this is a very brief kind of what's happening in our atmosphere. Atmospheric science does a lot more of this, and that's a whole other field. Astronomers just use this to kind of model what's happening on other planets. Okay. So we're going to get a little more in depth here. This will help us talk about the terrestrial planets, but we can also think about what's happening on the surface of Earth and how that might look from space, and just also what that tells us about how Earth has formed and changed over time. So I've put a few images here of things that might affect the surface of Earth, but also if you have ideas, what causes changes in the surface of the Earth? Why do we see different surface features? You can throw them in the chat. Like what do you think of when you think of features on the surface of the Earth? What causes changes? So water's a big one. I'm seeing that. Wind is another one. Plate tectonics is very important. So yeah, plate tectonics, we can get mountains like the Rockies over here where we two plates push together and one rises up. Rivers making canyons, kind of like the Grand Canyon. Maddie, volcanoes, that's another great one. Got St. Helens there because, you know, good volcano. So those are kind of the main things. We have water, plate tectonics, volcanism, and then also some wind, weather erosion kind of stuff as well. This is sort of wind erosion, a little bit volcanism and wind erosion in that middle one. And of course, the other one that I kind of tried to hint at on the slide is that life can change the surface of the Earth as well, whether that's humans cutting down, building roads, cutting down forests, whatever else, or plants growing up, holding banks together or eroding soil. Life can change the surface of the Earth. But yeah, water, plate tectonics, volcanism, which is related to plate tectonics, wind, and life are the main things happening on Earth. What's really interesting, and we'll get to this more next class when we talk about the terrestrial planets, but most of those things only happen on Earth. So water is only on Earth, life is only on Earth. Earth is actually the only planet with plate tectonics, which is interesting and could affect why there's life on Earth and not other planets. Volcanism happens everywhere, so that's the only one that we'll see everywhere. And wind also seems to happen pretty much everywhere. But Earth is a pretty unique place and definitely affects the fact that we can exist here, which is great.
Wait, why is Earth the only planet with plate tectonics?
It's a good question. We're not 100% sure. We think, or the kind of scientific theory is that it has to do with water. And so to have plate tectonics, which this slide kind of hints at, we need a liquid-ish layer underneath the crust. And so we need our mantle to be not quite solid. And it seems like the Earth's mantle is kind of, we call it a plastic. It's a solid that shifts very slowly over time. And it's able to shift because there's a lot of water in the minerals in the mantle. So because Earth has water, we get a mantle that is slightly plastic and not solid. So our inner layers are slightly movable, and we actually get plate tectonics. Other planets have less water, so they don't have that slightly mobile mantle, and they don't have plate tectonics. think that's the main theory now. There also might be a size component where you need a planet that's big enough to actually get your crust splitting up into layers. So you could kind of think of Mercury as a crust on a liquid mantle, but there's only one plate. So you don't see plate tectonics because there's just one big plate, because Mercury's small enough that you can get one plate, whereas the Earth has, I think, 11 different plates. So, good question. Obviously, it's still something we're trying to figure out. But kind of continuing on that note, the Earth does have layers. The first layer is the crust. There's two types of crust on the Earth. There's oceanic crust, which is underneath oceans, and there's continental crust, which is underneath the continents. The crust is about 3 to 44 miles deep, depending on where you are, and the ocean crusts tend to be slightly harder, slightly denser. So usually when you get to a border like at California, the ocean crust is going underneath, it's being pushed underneath the continental crust. And that's why they get a lot of earthquakes around California as these plates push against each other and cause friction when they push, and then all of a sudden something jerks. So usually right along coastlines, anywhere where there's a plate boundary, we're going to get a lot of earthquakes. The other thing to think of, so 3 to 44 miles might sound really, really deep, and humans haven't gotten through that even, so it is pretty deep. But if you were to shrink the Earth down to a size of an apple, the crust of the Earth would be thinner than the skin of that apple. So it's a very thin layer when you consider the entire Earth. So 3 to 44 miles, depending on where you are, but thinner than, comparatively thinner than the skin of an apple. So pretty thin. The next layer, and the biggest layer, is the mantle. So this is that plastic layer that's semi-movable because of, we think because of water. It's heated by pressure from the outer layers, pushing down and condensing things, causing things to heat up. The mantle makes up about 82% of the volume of the Earth. So most of the Earth is in this mantle, and it's where kind of the lava, the magma, when we get volcanoes, is coming from this mantle layer as things get heated up. And if you have a crack in your crust, you can get magma, lava pushed up through that crack and coming out in the form of a volcano. We'll also get to this in our next activity, but no human has made it down to the mantle, so everything we know about the mantle is either from measuring what's coming out of volcanoes or by using seismology. So we use seismology, we use the speed of earthquakes traveling through the Earth to figure out what the mantle is made out of. The next two-ish kind of layers here are the outer and inner core. So the outer core is it's like a liquid rock, so molten rock. And then the inner core is solid, so it gets so compressed. This is like a solid iron core in the middle. It's very, very hot, so it's, make sure I get my numbers right. The outer core has temperatures of about 9,800 degrees Fahrenheit and pressures over 3,000 times the pressure on the surface of the Earth. So pretty rough conditions down in the center of the core. The other thing that's really cool about the core is because of the rotation of this core and the molten layer, we have a moving conductor. So that molten metal, that molten iron is a conductor. So as it rotates, that rotation produces moving current, a moving conductor, which acts like a bar magnet. So any moving current produces a magnet, and that's why we have our magnetic field, is because we've got this molten iron core that's rotating around, which is another thing that allows for there to be life on Earth. Now, other planets in our solar system do have magnetic fields, so that's not unique to Earth. Anything with this molten core that's rotating with the rotation of that planet would produce a magnetic field, which blocks some of the harmful things in space from getting down into Earth. So those are our layers. You got the crust, the mantle, the outer core, and the inner core. And despite the fact we've never gotten through the crust, we can measure what's going on underneath it using seismology. And again, like I think we kind of hit on this, but yeah, we get seismology is possible because we have earthquakes. Earthquakes occur when the different plates push up against each other. There are 11 plates, major plates on the surface of the earth, and it's those plate tectonics, that shifting motion, that produces earthquakes and can also create mountain chains when we get two plates pushing up against each other. And you can get volcanoes along the separations between the plates. So with that, I want to take a little break here, or not break, but I'm going to put you back in your breakout rooms to do the Understanding Earthquakes activity. Just to give you a little overview before we get into that, the first part of this looks at earthquakes and where they happen. Hopefully with what we just talked about, it won't be anything too surprising. And it uses a little map to kind of show that. The second part is a little bit more complicated. So it's going to look at, we're going to look at how seismologists, what data they might work with and how they understand what's going on underneath the earth. So I've given you some data from a recent earthquake where we can see the shaking of the earth measured by seismographs over time, and then also on different locations around the earth. So 0 degrees is the epicenter of the earthquake, and then as you move around the surface of the earth, you get up to 180 degrees when you're on the exact opposite side. So with this one, what we're going to try to do is make a plot of location on the earth versus time that the earthquake is felt. So I've done it with a Google Sheet. You can do this with Excel. If you'd rather just make a plot in your notebook, that's also fine, whatever works. And then there's a spot where you can upload an image of that plot. So what you're looking for is when do we see kind of the biggest shaking happening? So when for each location is the biggest shaking? And when you get out really far away, it's very difficult to tell. So just do your best. But the idea is you guys are going to get to do the work that seismologists do to understand the different layers of the earth in this activity. So I will go ahead